All right, so welcome to the next session. As I introduced myself yesterday, I'm Adam Cohn. I'm the president and CEO of AUI, and in that role, I have to enable researchers and activities to happen to enhance and continue to propel forward the research. And I'm an engineer, and so I'm very outcome-oriented. So with that in mind, I stepped in to chair this session because I want to enable this workshop to succeed. So I am chairing this next session, and we have a 1 o'clock deadline for lunch, and I'm going to drive to that outcome. So
well, we are 15 minutes late.
I'm going to drive to that outcome. So with that in mind, I'm going to introduce Sun Kwok, who's going to talk about chemistry, and he has 25 minutes to present, and he wants 5 minutes for questions. So there we go. Go.
Right. Okay, what's organic matter? As soon as chemists found out that there are certain molecules that are responsible for the living organisms, those were believed to have special qualities. So there is something called vitality, which they think before the 19th century is what separated living matter to non-living matter like minerals or rocks and so on. Now, however, as soon as chemists were able to synthesize living organic compounds from inorganics, it was then believed that there is really no such thing as vitality, and we were able to give a new definition to organic matter, meaning it's just a whole system of molecules with carbon, oxygen, hydrogen, sulfur, phosphorus, or whatever. So now let's take a look at the amount of organics on Earth, okay? Because the organics were, if you think about it, most people would think that the biosphere may contain most of the organics. But in fact, it's not. Most of the organics are in the form of kerogen, which is a macromolecular substance found in sedimentary rocks, which consists of a mixture of rings and chains and so on, and the amount is far greater than the organics in the biosphere. So the question then becomes, are there organics outside of the Earth? Now, kerogen is actually biological in origin. It is the decay product of after millions of years of previous life, and they are the precursors of fossil fuels like oil and coal and natural gas and so on. Now, very small amount of organics on Earth actually is biological in origin. There are some methane gas from thermal vents and so on, but the great majority of the organics on Earth is biological in origin. Now, we have come a long way since that time. Now, actually, I'm going to summarize that actually today we now know that organic matter is everywhere in the universe, from the solar system to stars to interstellar clouds and also in the distant galaxies. So that started about 30, 40 years ago when we have the capability of detecting rotational transitions of molecules using millimeter wave and sub-millimeter wave spectrometer mounted on telescopes. As early as the 1950s, Swarovski and Charlie Towns proposed that there may be molecules in space, but at that time, no astronomer believed them because it was thought that the density of the space is so low and the ultraviolet background is so high that any molecules in existence would be destroyed. Now, of course, we now know that from empirical evidence that through the detection of both vibrational and rotational lines of molecules, we now know there are over 200 different kinds of gas phase molecules being detected in stars and in stellar medium. And that includes all families of organic molecules, from hydrocarbons to alcohols to aldehydes and so on. Now, this is an example of the spectrum. Please note there's no noise in this spectrum. Every part of this spectrum are filled with molecular lines. And we are running into a confusion limit. There are so many molecules, and our detection sensitivity is so high that we are completely filling up of the millimeter wave spectrum. Now the detection includes some prebiotic molecules, including some detected with the green band telescopes right here. There are some precursors to sugar, and also molecules that carry the peptide bond. Now the fact that some other biological molecules were searched but not detected is not because they are not there, but because we have the problem of both the partition function being too large. That means for complex molecules they are not symmetric, and the energy levels are spread all over the place, and the individual transitions are very weak. And secondly, the signals are being overwhelmed by simply molecules, like formaldehyde or whatever. So the question of the presence is not absence. It's not so much that they are not there, but they are. We are suffering from the problem of both line confusion and the partition function of the larger molecules. Now, the breakthrough really came in the solar system because as soon as we have the capability of sending spacecrafts to perform in situ observations as well as bringing samples back to Earth, then there are evidence of a large amount of organics in the solar system. But the question is that what is the origin of these organics? And that is the second question I want to address today. Now, these techniques include remote observations like using astronomical telescopes or sending mass spectrometers to the location, or even carrying the sample back to Earth for laboratory analysis. And the advantage of that is because we have many different kind of techniques at our disposal once we have the samples on Earth. Now, the easiest thing to do, of course, are meteoroids. Although there are evidence of maybe organics in meteoroids as early as the 19th century, the most strong evidence really came in the 1960s, and we now know that there are millions of compounds of actually every kind of organic compound that we know of has counterparts found in carbonaceous chondrites. And they include not only the normal kinds of organic molecules, but they have more than 100 amino acids, and that means they are more than the 20 that you use in living organisms. And the decreasing abundance relating to the increasing of the number of carbon indicates that these are not decay products of living organisms, but they were built up from simpler molecules. So we have amino acids, both of right and left-handedness, not just a single character. Let's say we have on Earth, we have nuclear bases detected more than the 5 that we use in our terrestrial biochemistry. So this suggests that abiotic chemistry, organic synthesis is actually very common in the solar system. The more interesting is the insoluble component of the meteoroids, because in this component we have an array of macromolecules which consists of a small number of aromatic rings linked by aliphatic chains, and they have mixed in other kind of elements like nitrogen, oxygen, and sulfur, and so on. And they make up 70% of all the organics in meteoroids. Now, comets are very easy to observe. They have a waterfowl component which you can do astronomical spectroscopy, and the more interesting are the cometary nuclei, where, for example, one can send missions to comets, and for example, the amino acid glycine were detected, and there are macromolecular compound in the cometary nuclei, which you can see, for example, evident by the 3.4 microns CH stretch, aphelic CH stretch, and which is similar to the spectral properties of kerogen, which is the most common organic we have on Earth. Now, in asteroids, they have some asteroids that are very low albedo, they have very red color, and their colors are similar also to terrestrial coal or tar sands or asteroids and so on, and they are indication that they may have covered in surface by complex organics. Actually, if you fly to a asteroid, you can again see the 3.4 micron feature that indicating of aphelic organics. Now, in the planetary dust particles, there's the advantage. You can use the airplane, you can collect these grains and bring them back to Earth for analysis, and similar kind of 3.4 micron feature can be seen. And we'll hear in the next talk about Titan. Titan has both in the atmosphere and in sand dunes have a large amount of hydrocarbons. In fact, it's estimated the total amount of hydrocarbons on Titan is more than the total reservoir on Earth. Now, in the news, we heard a lot in the last year or so about the detection of organics in the crater on Mars and also in the plumes from Enceladus, and these have been suggested to be biologically related, but actually they are not. They are just released product of macromolecular molecules similar to kerogen, which are embedded deeper in under the surface. Now, for Pluto, the New Horizons spacecraft have detected regions on the surface, which again showing characteristics of complex organics. So in summary, we now know that there are organics in the meteorites, in comets, in asteroids, in the planetary dust particles, in planetary satellites, in the outer objects in the solar system, and they are not nothing to do with life, but they are made from smaller components or through abiotic processes. Now, the next job I want to talk about is that whether these organics were made within the solar system or they were transported from somewhere else. Now, the only evidence that we have for direct synthesis of organics in the late stages of cellular evolution. Here we show that when a star begins to move off the main sequence, and after the red giant branch, on the so-called asymptotic giant branch, helium is burned into carbon. These carbon are dredged up to the surface. They first form simple molecules like C2, C3, Cn, and then these stars form a very strong stellar wind, and these stellar winds carry with them the molecules are further formed in the stellar wind to show how strong the stellar wind is. The winds are so strong that the amount of solid material ejected completely cover the photosphere of the stars, and the energy is completely radiated in the infrared. So from millimeter wave spectroscopy, we have detected close to 80 gas phase molecules that includes both rings and chains and so on, like cyanopolyeins. And so these stars are very prolific molecular fractures. There are also minerals like silicates and silicon carbide, which are commonly produced by these stars. And the most interesting is in the following phase after the asymptotic giant branch comes a phase called planetary nebulae, which are very upright objects. In the 1960s, a whole family of unidentified features were found in the spectrum of the planetary nebulae. They appear in wavelengths from 3.3, 6.2, 7.7, 8.6, and 0.3 microns. Those do not correspond to anything that astronomers knew of at that time. Very soon after, there were suggestions. There is a paper in Nature by Roger Neck that the 3.3 micron feature was due to the CH stretch due to aromatic compounds. But no one believed them at that time because astronomers thought that organics are so exotic and fantastic, they can never be seen in this medium. Now, they are not only seen in planetary nebulae, they are also seen in external galaxies, and these UIE bands are very common. They also carry a lot of energy, up to 20% of the total energy output of an active galaxy can be emitted in these UIE bands. So if they are organics, then it's a lot of organics. And the galaxies are seen as far as a redshift of 2. That means 10 billion years ago, we already have organic synthesis in the universe. Okay, so now, where do these organics come from? Well, we know that on the asymptotic giant branch, there were no UIE bands. They only appeared in the planetary nebula phase, and in between the asymptotic giant branch and planetary nebula phase, there is about several thousand years of unseen missing link, and that's what we call a protoplanetary nebula. So, in order to see what's the early stage of this organics group may be formed, we have to search for protoplanetary nebulae. So in the 1990s, Bruce Ripneck and I have discovered about 30 protoplanetary nebulae. Very soon after that, we thought, well, these are some examples of the protoplanetary nebulae that we discovered, and we follow up by spectroscopic observations, and we see that there is a 3.4 micron feature, which is appearing almost equal strength with the 3.3 micron aromatic CH stretch. Now, this 3.4 micron feature, as you look into the chemistry literature, it was well known by laboratory chemists because they've been studying organics in the laboratory. It's due to the either symmetric stretch or antisymmetric stretch of methyl and methylene groups. So we also, these are some schematics suggesting how these groups may be present around aromatic rings. We also found that there are very broad emission plateau features, about 2 microns wide each, at just center around 8 and 12 microns. And we suggest that these 2 plateau features are due to a collection of in-plane banding, which many aliphatic compounds have in-plane banding modes around 8 micron, or out-of-plane banding modes, which are around 12 microns, and we have a variety of different kinds of aliphatic side groups that is possible to create such a broad spectrum features through a superposition of all these bands. So how did it come about? So now the first ring, of course, is benzene. And we know that in the very late asymptotic giant branch, we have detection of acetylene. And acetylene is a linear molecule which, when they are bound together, they can form benzene. So benzene was detected in protoplanetary nebulae, so we have evidence that they have acetylene goes to diacetylene, triacetylene, and then on to benzene. And if the benzene rings group together, they can form aromatic molecules. And very interestingly, we have a very good constraints on the chemical time scale, because on the asymptotic giant branch, since there is a stellar wind, the chemical time scale is only about 10,000 years. In the planetary nebula stage, both the evolution and the dynamical time scale is about 20,000 years. So whatever happens of any chemical synthesis have to be happen within that time scale. There's also other advantages, because we know everything about the energy source, which is a star in the middle. We know the geometry. We also have independent means of determining the temperature, density, and also the radiation environment. And as I mentioned, we also have a constraint on the time scale. So we have to try to seek an explanation to this unidentified infrared emission bands phenomenon, which consists of all these components. So what is the carrier of these UIE bands? Okay, so in the astronomical community, it was very popular as a hypothesis called the polycyclic aromatic hydrocarbon pH hypothesis. These are very simple molecules of 2 elements. They are planar pure aromatic compounds. And he summarized in this review article saying that these UIE bands are due to cascades of the vibrational transitions after these pH molecules were excited by photons, and the number of carbons in these pH molecules are no more than 50. Now, however, there are significant problems with each hypothesis. First of all, these are simple molecules. The lines are very narrow, where the observed bands are very broad. And the pH molecules are well studied by chemists. They have very strong absorption in the ultraviolet, but they don't have much absorption in the visible. However, we see these bands both in stars of very low temperature, in reflection nebulae, in Pre-Planetary nebulae. And the most significant is that the pH molecules have very strong electronic transitions. And these electronic transitions have been searched for, but never observed. So the upper limit is 3 orders of magnitude below what was predicted if the UIE bands are due to pH molecules. Okay? So chemists are very unhappy because pH molecules are very simple molecules. They are well studied in the laboratory, and they say they find that there are no correlations that they can determine that about band positions and profiles and so on with the pH molecules. Now, so how do the people fit it? You read some astronomical literature, you look at the feeling. They say that they have excellent fit, but how do they do it? They use a large mixture of pH molecules of different geometries and ionization state to make them fit. Okay? So this is a summary of a sentence from a group from Berkeley. They say that the pH molecules do not produce the details of the rising spectrum. So, okay, so they're very kind to allow us access to the database as well as their routine, and we have used the routine. We try to use the routine. They can fit silicates, they can fit spectrum code. Basically, they can fit anything. So the model is really meaningless. Okay? So if they are not pH molecules, then what are they? It turns out that just by using 2 elements, carbon and hydrogen, and you mix them, then with different kinds of chemical bonds, you have a variety of amorphous solids that can result. And on this corner, you have a pure sp2 structure, which is graphite, on the one corner, which is diamond, and pH molecules are on the bottom. So in the laboratory, people have been doing experiments by mixing different gas phase hydrocarbon molecules. You bombard them with different forms of energy, with laser or electric discharge and so on. You collect the evaporated compound and into a cool substrate. You can do analysis on the substrate, and you can do spectroscopy on these substances to turn out that their spectra are similar or qualitatively similar of the astronomical UIE spectra. So what is the chemical structure of the carrier? So in order to explain all these observational properties, so in 2011 we proposed that the model of mixed aromatic and emphatic organic nanoparticles, which is a mixture of small units of aromatic rings linked by polyphasic chains of different lengths and orientations. And they are very different from the pH model because they are 3-dimensional, they contain impurities, and they are amorphous and not of a fixed structure. So this is a typical unit of a known molecule, and with this kind of, so you can see that it's very disorganized. And now we have been able to do now quantum chemistry calculations are so powerful, we're able to explore the vibrational modes of these complex molecules, because the chemists, once they understood the basic principles, they really had no interest to calculate larger molecules. But this can be done. Now, I don't want to go into the details, except that now, just to show some examples, by looking at these results of the calculation, we can identify what kind of vibrational modes are there and how they can be related to the observed astronomical phenomenon. I want to mention also fluorines, which have now been detected in planetary nebulae. They show the same kind of plateau features that we saw in the planetary nebulae. So there are questions being asked whether the fluorines are either byproducts of molecules. Now, in the diffuse interstellar medium, we have a very powerful tool of doing absorption spectroscopy. Because by absorption spectroscopy, we don't have to make any hypothesis about excitation mechanisms. The only parameter is the oscillator strength. So one can do a measurement and we can determine how much material is in your line of sight. So by analyzing the 3.4 micron absorption feature against the infrared source, we can determine that at least 15% of all the carbon in the diffuse interstellar medium is in the form of adiabatics. We can use this 3.4 micron line, we can map the galaxies, so they are everywhere. So they are not just aromatic. It's not true that the organic universe is only aromatic. They also contain a adiabatic component, and raises the possibility if stars are routinely able to manufacture and eject this kind of complex organic, they can spread throughout the Milky Way galaxy, some of which could be embedded into the primordial solar system. So I want to skip over this. Now, there is even a possibility some of these may have been embedded in the primordial Earth when it was first formed by accretion of planetesimals. So, because all the coal and oil are natural products of kerogen, so this if there is a primordial component which are structured with a molecular structure similar to that of kerogen, we can wonder whether there are, in addition to biological fossil fuels, there are other sources of oil and gas which could be beyond our current capability of exploration. So in summary, I just want to leave you the impression that organic compounds are everywhere in the universe, all the way from the solar system to distant galaxies. The detection of the UIE bands at distant galaxies suggests that even 10 billion years ago, we already have organic synthesis, and this bands phenomenon is consistent with the mixed aromatic and adiabatic organic nanoparticle hypothesis, and planetary nebulae and pro-planetary, they are the only objects that we have a direct observations of chemical synthesis going on. And these syntheses are taking place over a time scale of hundreds of thousands of years. So detection of these macromolecules are similar to those seen in meteoroids, IGPs, comets, and so on, will raise the question to what extent our current content, organic content in the solar system, have been contaminated by stellar ejectors. So I just want to leave with you a list of references, because all the technical details can be found in these papers. And thank you for your attention.
Questions?
Yeah, so in your talk, you mentioned that some big numbers. You said something like they're 10 to the 33 or 10 to the...
Oh, that's theoretical, theoretical.
So first of all, how was that number? There were like 60 orders of magnitude variation there.
I'm just quoting from references.
Right.
Yeah.
Okay, so how was that
So they would just say depending on how large a molecule you count. So just using the carbon, hydrogen, nitrogen. Yeah. You say theoretically how many.
Right. So anyway, there are a lot more than the type of organic chemistry we have on Earth. Are there any generalities you can say about the type of organic chemistry we have on Earth compared to what you see?
Well, the message I try to convey is that our terrestrial biochemistry could be just a very specific branch of all the biochemistry possible.
Can you be more specific about the word specific?
Any other questions?
Yes.
Penny.
So, I think the case for prebiotic synthesis, gas drains, and all these other mechanisms that you discussed is very good. But what I wonder is how much of that could we expect to survive through the relatively violent processes of proto-solar nebula
Yes,
formation?
okay. I didn't have time to go into this. The moon molecule compounds are very sturdy, okay? So, and we already have evidence of pre-solar grains we can hold in our hands. Solid particles made in asymptotic giant branch stars, in the form of minerals. So I think they can quite easily survive if these simple minerals can survive the trip from stars to the solar system.
All right, so let's thank our speaker again. And we'll turn it over to Martin to talk about ALMA. Talk about organic molecules on Titan.
Okay, thank you very much. It's a real pleasure to be here at this really interesting meeting. So Titan, with its carbon and nitrogen-rich atmosphere, is very interesting from the planetary science perspective to study processes, physical and chemical, that are going on in the vast array of probable hydrocarbon-rich worlds around the galaxy. Now, because of Titan's very thick atmosphere and liquid on the surface, you can draw analogies to the Earth. It's Titan's the only other body in the solar system that has a solid surface with bodies of liquid and a thick atmosphere. So by studying processes in Titan's atmosphere, we might be able to get insights into some of the things that were going on during the Earth's earlier history. So I'm going to present a very brief, 5-minute overview of what Cassini, during its incredibly successful 14-year journey through the Saturn system, has been able to tell us about Titan. Then I'll move on to just discuss a few of the results that we've been obtaining recently using the ALMA telescope. So the overarching theme of my research in this area is where did organic matter on planetary surfaces originate from, and what is the probability that similar kinds of organic molecules have originated on other planets in our solar system and elsewhere in the galaxy. So we consider two basic origins for the organic material, and this is as a result of the early Earth forming in a very hot and very inhospitable state for organic molecules to survive. And so therefore we need a subsequent delivery or in situ formation of organic molecules to give us like the starting point for the basic building blocks for prebiotic chemistry. So we have the possibility of exogenous delivery from comets, and this is ultimately stemming from the types of environments that Sun just discussed, where you have organics forming in nebula regions that can then be delivered to planetary surfaces by cometary, asteroidal or meteoritic impacts, and also from the arrival of interplanetary dust particles. We also have the endogenous synthesis route, where in liquid phase we can start with basic chemicals like water, ammonia, methane, add a spark or electricity or volcanism, some kind of heat, and give rise to organic molecules like were measured in the Urey-Miller experiments. And also gas phase processes which can be initiated by ultraviolet radiation or cosmic rays, can give rise to atmospheric organics that can then precipitate down to the surfaces. This is why it's interesting to study Titan. So Cassini and other space missions allowed us to peel back this, basically, it looks like an orange orb, and this is due to the extreme amounts of haze in the atmosphere. It's a carbon-rich haze, as it turns out. So, as we know, because Titan is one of the largest moons in the solar system. It's Saturn's largest moon. You see it in context with Saturn's other moons. Cassini has shown us that it has a water ice surface and a hydrosilicate core, and gravitational measurements have shown with pretty good confidence that there's also a subsurface ocean there waiting to be explored. About currently we really know very little. One of the really spectacular results from Cassini was the mapping of the northern latitudes and the discovery of these extensive network of lakes and kind of dendritic drainage basin type features. And this is showing us the prevalence of liquid methane on the surface. It's kind of a mixture of volatile hydrocarbons in these lakes, predominantly liquid methane and ethane. So it's really fascinating to study the surface processes on Titan. At mid-latitudes, we have what are believed to be organic grain-rich. It's basically a carbon equivalent of sand, which forms into these wind-blown dune features that line up with the wind direction. The compositions of these particles are not really well known, but they're believed to be very carbon-rich, and as a result of aerosol particles forming in the atmosphere and floating down to reach the surface and build up over time. If we're going to have any kind of communication between that subsurface ocean and the surface, we need to have some sort of cracks or fissures, and so it's been an active area to try to identify evidence for cryovolcanism on Titan, which is to say ice volcanoes, and this is probably the best evidence, and it's not really very good evidence that there might be cryovolcanoes. You can just sort of infer from the shape of this. It's a radar image showing like a mountain and some sort of patera-like incision into the surface. We don't know how deep that goes and whether there might actually be any communication between that subsurface ocean and the surface or not. So I'm a little bit more interested in my research in Titan's atmosphere. It's, as I mentioned, it's predominantly a nitrogen atmosphere. It has a lot of methane as well, about 2%. It has a very high pressure. It's higher pressure even than Earth's atmosphere at ground level. The methane in the atmosphere undergoes a sort of cycling where you have methane clouds and rain, and then subsequent evaporation to give rise to a methane cycle on Titan, analogous to Earth's water cycle. Getting into the nitty-gritty of the chemistry, this is a Cassini ion mass spectrum taken from quite high up in Titan's atmosphere, and as a function of mass you see the various peaks, and they're all labeled here. An absolute wealth of different organic molecules. This is predominantly showing hydrocarbons and nitriles, because those are the most likely species you'll form from the nitrogen and methane atmosphere. And in fact, you can construct elaborate chemical models for these gas phase environments. This is just showing an excerpt of the hydrocarbon chemistry, starting with methane, photolysis, and adding hydrogens and carbons. And on the right, you get sort of the end products, different carbon chains and interesting organic species. So we build up this picture of high altitude energetic processing of the nitrogen and methane, building up molecules which then get larger as you go down to higher pressures, and they begin to sink under their own weight in the end and precipitate out on the surface. Measured using the INMS, the ones in italics, actually the protonated versions were measured with this instrument. And so you take the proton back off, and then you can say that these species are present. Exciting species like the carbon chains, nitrogen-bearing rings, and other complex organics are being formed there. And it's not a far cry to say, you know, that these kinds of, particularly nitrogen heterocycles, bear more than a passing resemblance to the kinds of pyrimidine-based molecules important in DNA. And methylamine has been postulated to be a precursor to glycine as well. So the links with biomolecules here are quite strong. And it just goes to show what the wealth of organic content of Titan's atmosphere is. So while Cassini did an amazing job spending 14 years in the Saturnian system, mapping out in detail all these different hydrocarbons, giving us really detailed, nice maps of everything so we can study the chemistry and dynamics, all good things have to come to an end. And Cassini was crashed into Saturn after its end of mission when the rocket fuel expired in 2017. However, all is not lost. From the perspective of studying Titan, we can turn to our valued Earth-based assets. And in fact, ALMA turned out to be an excellent tool for studying Titan. In case you're not familiar, it's a radio wavelength interferometer located in Chile at high altitude, so it's above most of the water. It wouldn't work really so well if you put it here in West Virginia. It works much better on a mountain top in Chile, and it's got an enormous number of dishes and a huge collecting area, which gives it unprecedented sensitivity for interferometric mapping and high-resolution spectroscopy to detect rotational emission lines from specific molecules. In particular, things like polar hydrocarbons and nitriles. The high resolution meant that ALMA has been revolutionizing a lot of different fields of astronomy, allowing it to map various different astrophysical environments from protoplanetary disks to galaxies, but it's also powerful for solar system bodies. So one of the things we did with ALMA in synergy with Cassini's grand finale, so final close flyby of Titan was on April 22nd, 2017, and then it proceeded to do this series of daredevil dives in between Saturn and its rings. And the final flyby of Titan, where it was doing full hemisphere mapping that we can compare with ALMA, was on May the 24th. And so we targeted this time window to do some detailed ALMA studies of Titan, of various organic molecules listed here. So I'll just show you some of these data, just give you a dose of some real planetary science. You see the spectral emission lines here in the sub-millimeter wave spectrum. Molecules like cyanoacetylene, acetonitrile, vinyl cyanide, ethyl cyanide, all very nicely detected, and we map out their distributions as a function of latitude and longitude on Titan. We're able to see strong peaks of these molecules at the poles, and what this is showing us is the result of Titan's high-altitude global circulation system, where photochemistry occurs mainly near the equator, high altitudes, stimulated by solar radiation, and then there's a huge Hadley-type circulation cell that channels all of those photochemical products towards the winter pole. And so obviously this shows you that these species are quite short-lived, because over long periods of time you'd expect them to mix back into the atmosphere and become uniformly distributed, but because their lifetimes are only of the order of a few Earth years, they start to break down again. And so you can basically track Titan's seasonal cycles by observing these kinds of patterns. Looking at only the spectroscopic detections now, because I'm a real spectroscopist, not a mass spectroscopist. A bit biased there. With ALMA, we've basically added to this list of known molecules with the ethyl cyanide and the vinyl cyanide, and we hope that it won't be too long before we can add more to this list. The vinyl cyanide was quite an interesting one from the astrobiological perspective, and it got quickly picked up on by the press. And this is an excerpt from one of the articles that came out. That's the one step closer to proving life can exist on Titan. So you're probably wondering what the hell this is all about. especially when you see a title like this. What this is because it was realized in 2015 from a study at Cornell University. It's basically a liquid phase simulation. They found that the vinyl cyanide molecule was the best candidate molecule on Titan for producing stable membranes in liquid methane. And that's quite an interesting result, particularly because at the 94 Kelvin surface temperature of Titan, your Earth-type phospholipid-based membranes are far too fragile and they just break apart, whereas these kinds of nitrile-based membranes actually remain flexible. They form as a result of the strong dipole moment of these molecules that they start to interlock head to tail. It's actually the polar end that ends up inside as opposed to the outside in the Earth-based phospholipid membranes. But I'd add that these definitely need lab confirmation before we can believe that these so-called azotosomes exist. So how do these molecules, we observe them in the atmosphere. I just want to make the point here that it's well known that from theoretical modeling, everything goes away in the lower atmosphere, and that's because it precipitates out of the gas phase. We've got methane clouds and this methane cycle, and clear evidence for rivers on Titan's surface. So we're able to get these atmospheric produced species down to the surface and put them into liquid. Little back of the envelope calculation, just for fun here, comparing one of Titan's seas to Lake Superior, you see for scale. We're talking about large bodies of liquid here, but they're up to 1 kilometer deep, so we have a lot of potential for chemistry in these lakes. Based on the net precipitation rate of the vinyl cyanide, so it's all precipitating down and mixing into the lakes. So we can take the ethane molar fraction and work out the total mass of vinyl cyanide in the lake. It turns out that there's so much actually it reaches saturation, so it can't, the liquid's fully saturated with vinyl cyanide, and at that saturation point, if we assume an azotosome size of 10 microns, then we get a few times 10 to the 7 per cubic centimeter of these little theorized cells. Thanks. I'm not really going to have time to talk about the real implications of this biologically, but of course you need much more than, on Earth a cell is a crucial part of the biology as we know it, and indeed probably quite useful if you're trying to get life going to have a compartment inside which you can concentrate your reactants and allow you to possibly remove waste through various ion channels. So the real open question is, if we form one of these cells on Titan, what other molecules can we use to serve as transmembrane proteins or ion pumps? But it's a far cry from having a real cell on Titan. And of course, anybody who's got a laboratory that can do these kinds of very low temperature methane vinyl cyanide experiments should do so to see if they can actually see one. A series of experiments on it, I think it was by Sarah Horst. She did nitrogen, methane, CO, which are all prevalent in Titan's atmosphere, and you have the formation of possible information-bearing molecules that are found in terrestrial DNA. Could pretty easily form under Titan-like conditions. So it's quite exciting that the true array of organic chemistry that you can produce as a result of abiotic processes on Titan. Out of time, so we have Titan's surface, very interesting chemically. We have the subsurface ocean. It's currently an active area for research as to the degree to which these two can communicate, to understand whether any of that rich organic inventory can be produced down in the subsurface ocean and mixed in to maybe help get life started down there. I haven't really got any more time, but I was going to play this. It's quite short. So 2 weeks ago, ago, we found out that Dragonfly was going to be Saturn's next mission. And it's going to be a really exciting way of further exploring Titan's surface chemistry.
All right, one quick question, then we'll break for lunch.
You talked about a lot of photochemistry that happens in the upper atmosphere. What are the wavelengths of the light? Is it UV that's doing that, most of that?
Yeah, it's solely UV, yeah.
And what about the chemistry that's going on the surface? What's driving that?
A lot of the UV is attenuated, but not all of it. So there's believed to still be some, like, I don't know, 200 to 300 nanometer radiation that's still getting down there.
At the surface of Titan?
Yeah, it's quite weak. I mean, I don't know if there's a whole lot getting to the actual surface, but the stuff I talk about here is very much upper atmosphere, where there is a lot of UV, and I know it gets down to the lower levels of the atmosphere, but I don't know about the actual surface if there's much radiation left at that point.
I have a couple just quick announcements before we break for lunch. First of all, the control room for the Green Bank telescope and the telescopes on site is directly above us. And anybody that has a blue tag on here can take you up in small groups to take a look at it. It takes 5 or 10 minutes and can easily be done during a coffee break. Just contact one of us. Secondly, the flash talks yesterday were so popular that we've had demand for another session, which we can fit in on Tuesday morning. So if you have other single slides that you want to spend a minute talking about, please send them to me. And then finally, where's Will? Okay. Will is in charge of the tour tomorrow morning. He has a few words about that.
Sure, a quick announcement. So we will meet tomorrow morning at 8:15 to head down to the telescopes and see the site. Anyone is welcome to join on this tour. We'll be back by the 10:15 session. A couple announcements about what to wear. So closed-toed flat shoes are required. No flip-flops, no heels. And then we also recommend long pants because there is grading all over the telescope. And there could be people working below you. We also don't want you to fall and scuff your knee on that grading. So we will meet at 8:15 outside of the residence hall. You can leave all of your electronics there. We'll bring the bus back so you can pick up any electronics before the first session. We will also stop on the way back for a picture at the Table telescope, which was used for Project ALMA, to take a picture with everyone. So, all right, thank you.
It may be working, I don't know. And I will begin to try and tell you my view of how we can try to connect the chemistry of planet formation to planets themselves. And so, intrinsically, how planets are born, that's an important question. What I would like to know is if we look at the composition of planets today, can we relate that back to the composition of Earth in whatever way? And what do we learn from the evolution of the planet from that process, or from that thought process? And, ultimately, we'd love to know how to make an Earth and know whether what we are, it's a preordained outcome, or maybe Venus is the expectation value. And of course, the importance of Earth is life. And today, I think astronomically, it's exoplanets are just exploding. The facilities that we have access to are just fantastic, and we're now able to grapple with planet formation in tandem with planet discovery, and that's an incredibly exciting time. I wanted to give context before I get rolling here. So this is a filament, a gas filament. It's about 20,000 astronomical units wide. So 1 astronomical unit is one Earth-Sun distance. That is a star that is being born right there. And this isn't the same object. This is just a bluff of what an object would be. That's what we call a protostar, where the disk has formed. This is a picture of the disk from the Atacama Large Millimeter Array. This is a Hubble Space Telescope image. And so the disk is accreting material from this natal envelope, and eventually the star dissipates the natal envelope, and what you get left with is a planet-forming disk that is exposed to space. All right, this is the phase, the gas-rich phase. This is a picture of a emission line from a gaseous molecule Gas giants are born during this phase. It's about 1 million years after this. And terrestrial worlds are born sometime a little bit after this phase, on the order of 10 to 30 million years. And of course, ultimately we get to planetary systems, and I just love this image because it shows a planetary system elsewhere in motion. Okay, so the way I approach the problem of formation of planets is not to ask, like, if you want to think about the origin of life, right? If I can make an amino acid in space, well, if I supply it to the Earth, does the Earth just break it apart? What happens to it? I don't know. So I just want to follow the carbon, and I want to follow the oxygen. I want to trace bulk abundances and follow what happens there, okay? So focus on understanding bulk composition. So ratios like the carbon-to-oxygen ratio, the total abundance of carbon, the total abundance of oxygen, and so on and so forth. Nitrogen is difficult to retrieve in exoplanets. We can get at it in planet-forming disks, but it also is difficult to get at. And for the solar system, we can get into the nitty-gritty details, but I'm not going to go there. So for gas giants is where I'm going to start, and then I'll get to terrestrial planets. At the base level, what you think about is if we think the core of a many Earth mass core forms first, and then it accretes a gaseous envelope. So under that construct, right, the core forms from what the solids are, and the envelope forms from the gas and reflects the gas composition. And I can observe the gas with instruments like the Atacama Large Millimeter Array. So if we want to think about composition, we have to ask where things are. So I'm going to break it apart between refractory materials. These are things that are hard to destroy. So there's the silicates, that's about 1400, 1600 Kelvin, they get destroyed. Refractory carbon, that carries about 50% of the carbon in interstellar space. That is destroyed, I think, around 400 Kelvin, maybe 500. If we go to what we call the volatiles, so this is a picture of the volatiles on Pluto, these things they're difficult to get into the solids. They are in solids, in comets, for example. So water ice, that's like 200 K. CO is 20 K, very hard to get into solids, but it's there. CO2, this is what carries the oxygen in the volatiles, and this is what carries the carbon in the volatiles. Whereas all of the O, there's a significant portion of O in silicates, and again, about half of the carbon is in some sort of refractory form, and Sun Kwok talked a lot about that. Okay, so for relating bulk composition to gas giants, if we want to think about, I have my star over here, and this is distance from the star. It's hotter and denser in the disk, closer to the star, so there's a density and temperature gradient, so hotter here, colder here. The most volatile substances are the ones that will have their ice lines, their vapor to gas transitions further to the star, and then I can work my way in. So this is a construct that Karen Oberg, Ruth Mary Clay, and I wrote a paper on that. If you just think about it, just simply about where the major volatiles are, the refractories stay in the solid state. If I'm right here, this is the CO snow line in the disk. Okay, my gas has CO in the gas, and the water and the CO2 are in the solids as ice. So if a gas giant is born here, it has a CO ratio of 1 in its envelope at birth. And if it somehow stays that way throughout its evolution, we can maybe measure it, and maybe I look at this, I can try and figure out whether it moved from here and migrated inwards to somewhere else where the CO ratio might be different. For example, if I go interior to the water snow line, everything comes back from the gas, and the CO ratio goes down to something like 0.6. Okay, so I can use the composition as to where a planet is born to maybe observe a planet and trace back something of the migration history, for instance. There are other complications to that I'm not going to get into, but at birth, this is certainly the case. Now, this is the existing landscape today. This is not anything to do with the chemistry, but it sets the physics of the system. And there was a beautiful ALMA large program, over 100 hours, that observed the thermal emission from solids in about 15 to 20 disks or so. And what I'm going to show you here is all those disks. And so this is the emission of millimeter-sized particles that are basically building blocks of planets. And as you can see, if you observe this, there's significant structure here. I see a lot of gaps and rings. A spiral is going to show up here. All right, so there's an awful lot of going on with the physics of planet formation that we're seeing in these images. All right, for the ones that have rings, such as this one that's cycling out, the prevailing theory for the origin of that structure you're seeing there is that there's a planet present, and it has carved a gap in the disk. And what you're seeing is the influence of the planet on the disk itself. And so this is a plot of planet mass relative to Jupiter mass versus radius. These are the exoplanets that have been seen by a variety of other techniques. These are the ones that are being inferred today from the ALMA observations. Now I want to state, this is one interpretation, and if you were in an ALMA meeting, there were other people and theorists who say, no, I can take my theoretical model and turn a couple knobs and I can match these observations. But this is the state of the art today. These planets, as they were born, they would actually migrate inwards. So it's interesting, we're inferring a new population of planets at greater distances. Okay. This talk is about chemistry. So I have to show you something about the chemistry. This is the thermal emission from dust in the closest disk, TW Hydra. So this is emission of a deuterated form of hydrogen cyanide, C2H formaldehyde, methyl cyanide. And what you see is that there's an awful lot of chemical structure. There's structure in there. What that is, there's some interaction between the physics and the chemistry of the system. Things are changing. That means chemistry is active during the phase where the building blocks of planets are being assembled. So that's kind of cool. That means we have something to do, and I have a job, right? This is another system where we see two gaps. We think there's a giant planet in this gap, another giant planet here, and actually another one further away. And again, we see significant structure. Now, with the dust, those pictures I showed you are amazing. They have about 5 to 10, probably 10 AU resolution. That is, each pixel on the image is 10 astronomical units. That's the dust. With the gas, it's harder to get that spatial resolution. And these images that I'm showing you here are about 2 to actually 3 times what we were able to get with the dust. We now have an ALMA large program that is taking data, I hope, as we speak, that's going to attain the first high-resolution images. So today, what I can tell you is that in the regions where those planets are being born, way out at tens of AU, the C-to ratio is indeed commensurate with our expectations from theory. It's at least 1, it may be a little higher. And within a year or so, I hope I can tell you something more about what's going on interior to that, where the giant planets are being born. But this is just beautiful, beautiful stuff that's happening. Now, the biggest result we've gotten from chemistry is a little bit harder to tease out, but I'll try and explain it to you. That is the mass. Now, there's just an accident of physics that hydrogen, the most abundant molecule in these systems, is unemissive at the temperatures and densities, well, temperatures, where the disks, most of the mass is present. So if I'm a chemist, I want to measure an abundance, and I can't get my hydrogen, which is what I'm going to measure it relative to. So this is a problem throughout all of the study of molecular astrophysics. And what we do is we use proxies. So the first proxy is we use that dust emission. Those maps that I showed you there, we have ways of converting that emission and measuring the dust mass. All right, and then I know from other calibrated observations that in the interstellar space, I just multiply that by 100 and I get the gas mass. Woohoo, off I go. Problem. If you look at the dust mass that we're measuring in those ALMA images, it's much, much less than the mass needed to form the planetary systems that we are observing. So what's going on? Well, we are observing millimeter grains. If you make grains that are a meter size or kilometer size, planetesimals, I can't detect them. So, okay, planets are being born in these systems where I just told you planets are present. So we're missing mass. So that my dust has a problem. Another way to get about it is to use 12CO. Carbon monoxide, we actually know its calibrated abundance in the interstellar medium. I observe that, voila, I multiply by its abundance, and I can get a mass. If that's true, then every disk that we observe to date can't make a single Jupiter at 1 million years. That can't be right. So I was very fortunate to go fishing with the Herschel Space Observatory, and I was able to detect hydrogen deuteride. Hydrogen deuteride is just H2 with a D instead of an H. And I know the abundance of HD to H2. So I can then use that to measure the H2 mass. And what we find out is we have only 3 detections, but it shows us that our calibrated CO abundance is wrong. That is, the carbon monoxide that we think should be present is actually, we think, locked up in solids. And I'll show you how that's happening and what we think that means. What about water? So while we were looking for hydrogen deuteride with Herschel, we also were looking for cold water vapor. And Lynn showed this image earlier. And when this spectrum came to us, I was super happy. We detected water in a planet-forming disk. And this is cold water. This is water that's emitting beyond its snow line. And what we found from that, and indeed we surveyed a bunch of systems, so just like CO, we are missing water. We have an expectation that some small amount of water vapor should be present beyond its snow line, and it's not there at the abundance that we expect. So there's a systemic thing happening to the chemistry that's associated with planet formation. So what's happening? Okay. Well, we have a system here. We have small grains and larger grains. As you get down here, here's my snow line. All right, the disk is hot, getting colder here. It's also hot on the surface and gets colder here. So there's a snow line here, but there's also a vertical snow line. All right, so I have my molecules in the surface. They get cycled down by a little bit of turbulence, and they start interacting with this stuff here, and they freeze out. The dust is doing something a little bit different than the gas. When the dust gets to a millimeter, 100 microns or so, it becomes decoupled from the gas motions. And the dust likes to go to where the gas pressure where the pressure is at a maximum. And so what the dust does is it settles to the midplane and it drifts inward. Okay? So that means all of my big dust, those pictures I showed you, that dust is not distributed the same way as the gas is. It's actually stuck in the planet-forming midplane. And that's good. We need that actually to make Earth-like worlds. That's where I think our solids are, and we have models that have shown that. So just to show you this pictorially, because we have ALMA and I can do that, this is a Hubble Space Telescope image of a planet-forming disk. What you see is the flared surface of this disk, and this light here, the white light, that is light from the star that is scattering off the surface of the disk. Okay? And this is the jet, so the system's accreting, and it's also releasing material.
Size?
And it can't release it from anywhere else, yeah?
How big is this? An AU?
I think I have a scale in a minute. Here, there we go. So this is, the ALMA beam is about this thing, so this is about 36 AU in this dimension. Okay, so this is the 12 CO emission, this is the gas, and the small dust, the micron-sized dust, that is lofted up with the gas, that's what's reflecting this or scattering the starlight. So you can see the CO sets the shape for what this disk is. If I look at the large grains, they are all super spatially concentrated to the midplane. That's planet formation. That's the beginnings of planet formation, and we can see with our own eyes. That's super cool. All right, so I just told you that I'm taking all of the carbon that I expect to be in the outer disk, and I'm freezing it out onto grains, and it's stuck in the planet-forming midplane. I also told you that this material will settle to the midplane and drift inwards. So what that means is that I have material, basically comets, that have an awful lot of carbon. A lot of carbon, almost all of it. Probably a lot of nitrogen too. And it's going to drift inwards and head to the planet-forming zone. And we have to figure out what? All right, so let's figure out what happened for the Earth within that construct. So here's the Earth, all right? The Earth is, this is interstellar mean. This is half of the carbon in interstellar space is here, okay? If I go to comets, comets have this carbon. And I go to meteorites, these are primitive meteorites, they are missing the carbon. And if I go to the Earth, the Earth is missing the carbon. The Earth got one carbon atom out of the 10,000 that was available. The story of planet formation is the story of carbon loss. All right? And what do I think happened? What must have happened is I had to somehow destroy those carbon grains. And that can happen if you do it early, when the system is warmer, and I can ablate the carbon grains, throw off all those volatiles, stick them in the gas, and you make the silicate rock that we're sitting on. All right? If this process is not happening, we would be on a carbon rock. All right? And that's a really interesting fundamental question that we have to solve. The other thing we have to do is we have to stop the drift from coming inwards. And you can do that by just having Jupiter form. If you form Jupiter, you reverse the pressure gradient, and the dust just piles up outside of Jupiter. Both of those facets, the materials of the Earth forming early, and the fact that Jupiter likely formed early too, are consistent with interesting results that just came out in the meteoritic community. So I'm out of time. I'm just going to skip to the summary here. Bulk abundances, I think, are a really key tool to understanding planet formation. And the Earth actually has information on its own history. We need to interact with Earth science. And if we can understand this process of how carbon gets supplied to terrestrial worlds, we can then start to think about predictive models for what we might expect, or certainly we can try to match what we're observing. And I think for giant planets, the links to formation are an emerging subfield. And this is just fantastic where we are today. And I can't show it because I don't have time. I knew I wasn't going to have time. But we actually just detected flows that are falling into the giant planet forming zone. We are witnessing the dynamical, like basically the infall of material on the forming giant planets. And that's a new result that will come out in a couple of months. Thank you very much.
Ted, I read somewhere of the speculation that the discrepancy between the measured mass and what's needed for these disks implied a kind of continuous flow of material into these disks during the planet-forming phase. But you would seem to indicate that, in fact, the discrepancy is not real.
That is correct. So the alternative, okay, so either the disks are missing carbon and you have to put it somewhere, or the disk is missing everything and you've blown away all the gas much more quickly. In other words, the gaseous disk is gone. So not only there's no carbon, there's no H2 as well. So there's two possibilities. There's no everything, or there's no carbon, but H2 is present. The disks are accreting with an accretion rate that suggests that over 1 million years, they need to have the amount of mass that is measured with H2 being present. So that's another line of thought. But I think with our observations of hydrogen deuteride, it's hard to get around the fact that you have a problem with your calibrated tracers of mass.
Ted, in the sun, solar composition, C to O is about 1/2, right?
That's right.
So in the outer disks, C to O is greater than 1 because the oxygen's tied up in water ice?
That's right.
Okay.
That's right.
One last.
Yeah, in the previous plot, could you show that? I wanted to know where the sun was on that C SI
Sure.
ratio.
So this is, I'm sorry,
Oh,
this
there
is
it is.
carbon to silicon. So the sun's over here. So you can see that the Rosetta, Halley, and the interstellar medium, basically they have the carbon that we think is there. It's all of the solids in the inner solar system that are missing that carbon. And it's whatever this process is, and I think I have an idea for what it is, it could be variable. And so that suggests that there could be significantly different levels of carbon content in terrestrial worlds. Or maybe everything just gets stuck in the outer disk and all forming planetary systems get the carbon just titrated very little bits. We're going to find out, which is kind of neat.
Well, let's thank Ted again.